Hello, differential equations. I wanted to, there's one last topic. If we move into chapter 8, we can do just a little small bit of chapter 8, which involves matrices. So first video here is a little matrix review. So that's a matrix. It's a 2 by 2 matrix. It's 2 rows and 2 columns. That's why you say 2 by 2. You say the rows and the columns. 2 rows, 2 columns, 2 by 2 matrix. Sometimes people use this for a matrix, but you can use these big parentheses, either notation. If you use this, that's not a matrix. That's actually the determinant of a matrix, which is a number. Just for fun, let's do that. So this is the determinant of a matrix, and if it's a 2 by 2 determinant, it's pretty easy. It's 12 minus -2. It's 12. You multiply that diagonal, subtract that diagonal. So the answer is 14. It is a number. When you were living in this world and working with matrices, they're different than numbers. And so the word we use for a number, the real numbers that live on the real number line, we've worked with numbers all our life. Well, now that we're working in this new area of mathematics with matrices, we call those numbers scalars. So those are scalar quantities. If you're a number, you're a scalar, and otherwise, if you're a matrix, you're a matrix. So can you take a matrix and add it to a number? No. Cannot do that. Can you take a matrix and multiply it by a number? Yes, you can, a scalar. So can you take a scalar and multiply it by a matrix? Yeah, you can. And the way you do it is you multiply every entry of the matrix. So it's like you distribute it times the whole matrix. So it would be 18, 12, -6, 24. I think I did that right. You can multiply a scalar times a matrix. Can you take a matrix and can you add it to another matrix? Well, yeah. Only if they're the same size, 2 by 2 and 2 by 2, because you add corresponding entries. So when you add matrices, you add the corresponding entries. What that means is the first row, first column entry gets added to the first row, first column entry. So, and anyway, you get, of course, 5, 2, -6, and 8. I think I added that, right? Add those, add those, add those, add those. Yep. You know, you can refer kind of arbitrarily to these. Well, anyway, let's do one more thing. So let's see. Can you multiply matrices? Yes, you can. And that's the big new idea. Let's do that here. It's not a new idea. I'm reviewing matrices, but this is the big idea. This gets a little funny. You take, to multiply matrices, you take that whole first row and you multiply it by that whole first column. And you multiply corresponding entries and you add them. So here you go. You go 3 times 2 is 6 plus -10. And then that's -4. And you put that answer in the first row, first column place. So, because you multiplied the first row times the first column, that answer, -4, goes in the first row, first column spot. So now you take the first row and you multiply by the second column. And you put that in the first row, second column spot. So that's, what is that? 3 times 0 plus 2 times 4. So that's 0 plus 8. It's an 8. And that goes here. Takes some getting used to. Here we go. Then we're done with the first row. We took the first row times every column. Now we take the second row and multiply by the first column. And that goes in the second row, first column spot, of course. Here we go. That's -2, -20, and we add that up. -22. Here we go. First row, second column. Second row, second column. That would be a 0 and a 16. We add that up. We get 16. So that's how you multiply matrices. and that's important to know. Of course, all this gets a little worse when you have 3 by 3 matrices or 4 by 4 matrices. You know, you can also have 2 by 3s and 5 by 2s, and you can have other matrices. Often they're square matrices, though. Often they are. Okay. One place they're used back in algebra is like this. Is you have 3x plus 2y minus a negative x plus 4y equals 5 and equals 6. So you have 2 equations, 2 unknowns, or 2 equations, 2 variables. It's a system of linear equations. And exploring the theories behind this is called linear algebra. There's a whole subject exploring, and you can work with matrices to do this. Of course, you've learned how to do this, just a 2 by 2. You've learned to do algebraically. We could get this answer in 2 minutes, but we're going to do the long matrix approach here, because it works for 3 by 3s, 5 by 5s, 5 equations, 5 unknowns, 10 equations, 10 unknowns, and you can probably sort of see the way a computer program could help you with these kind of problems. All right, so let me explain this to you. What we have here is a system of 2 equations, 2 unknowns, but you could write this in matrix format. What you have is the coefficient matrix 3, 2, negative 1, 4 multiplied by the variable matrix xy, and it equals the answer matrix 5, 6 here. Now these are little 2 by 1 matrices over here. Sometimes they're called a column matrix. I'm sorry, yeah, a little column matrix, but also they're called a vector. It's a vector. It's, I mean, I know I'm used to writing vectors like this. There's a 3-dimensional vector, but if I'm operating on a vector with a matrix, I would write that vector like this. And so anyway, that's language, some language there and some connections. So sometimes it's called a column matrix or a column vector or a 2 by 1 matrix. Anyway, do you understand that if I multiplied this, if I applied those rules, 3 times the x plus 2 times the y has to equal that entry 5, which is what this says. 3x, 2y equals 5. This row times this column, the negative x plus the 4y has to equal that entry, the 6, which is what that says. So I'm rewriting this in matrix form. And then what you do algebraically is you think of it as kind of an algebra problem. You use capital letters to represent matrices. And so there's a capital letter matrix A multiplied by the variable matrix X. And it equals this answer matrix over here, B. So if you're doing algebra and you have A times X equals B and you're looking for X, what do you do in algebra? You divide by A, okay? Well, in matrix world, we don't really have division, so we don't divide by A. And just to go back to good old straight multiplication, if you had back to real numbers and real number multiplication, you would say divide by 3, but another way you could say that is multiply by his multiplicative inverse. So you could multiply by 1/3, which is division by 3. But in matrix language, there is no such thing as division, but I can multiply by his multiplicative inverse. And so I would, but the funny thing about matrix multiplication is that it is not commutative. It is not commutative. So when I multiply by A inverse times A, I'm multiplying on the left. And therefore I have to multiply on the left, A inverse times B. Because it's not commutative, matrix multiplication is not commutative, I can't just multiply on either side. So now there's a thing called left multiplication and there's another thing called right multiplication. You know, when you do multiply by 1/3, it's the multiplicative inverse of 3 and you get what's called the you get a 1, but that's the identity element of multiplication. So you get a 1 times x, and the identity element is awesome because what's 1 times x? It's just x. So, so that's what happens in matrix world. When I multiply A inverse times A, I get the identity element I. That's the identity matrix I times x. And what is I times x? It's just x. That's the definition of an identity element. So the answer is this A inverse times B. Now the problem is finding A inverse. We have A here and we have B here, but finding A inverse is kind of a pain. It's kind of a long process. By the way, let me just pause here. I talked about this I real quick. The matrix I is this. For a 2 by 2, it is this 1, 0, 0, 1. It's ones down the diagonal, zeros everywhere else. So finding A inverse, that's going to be a little tricky. So I think I've memorized this formula. For a 2 by 2, it works like this. A inverse is, hang on, I'm sorry. If you have, this is the formula. If you have a matrix A, B, C, D, then A inverse is, you switch the A and the D, D, A. You negate the B's and the C's, but you leave them where they are. But you negate both of them. Switch the A and now that's an O. And you multiply out front by 1 over the determinant of A. Sorry. Let me clean that up a little bit for you. Sorry about that. 1 over the determinant of A. So that's A inverse. That's a little special formula I learned for a 2 by 2. Okay, I can try to do this. Let me try to find A inverse then. So A inverse for this problem is, there's the A right here. So A inverse would be, what did I say, switch those two? So that would be 4 and 3. Negate those two, so he becomes a positive 1 and a negative 2. A positive 1 and a negative 2, yeah. Oh, and out front though, there's 1 over the determinant of A. And we did the determinant of this a little earlier. The determinant of this is a number. The determinant of A is 12 minus negative 2. 12 minus negative 2, that was 14. So out front here is a 1/14. So technically, if I distribute that, A inverse is this. 4/14 or 2/7. Negative 2/14 or negative 1/7. 1/14 and 3/14. That's the inverse of this matrix. That was cool. All right, I'm going to get rid of some of this. I need a little more room here. All right. So now the point is, if I follow this algebra, what I want to do to get x, the unknown matrix x, which is this little x and y, I should do that A inverse. Here it is, 2/7, negative 1/7, 1/14, 3/14, and I should multiply it by B, which was this 5 and 6. So I'm doing what this told me to do. All right, and when I do this, I'm multiplying a 2 by 2 by a little 2 by 1. I think I'll take that row, multiply it by that column, and I'll put that answer here in the first column spot. My answer is going to be an x and a y. My answer is this variable matrix x. All right, here we go. That's going to be 10/7, negative 6/7. When you add that, that's 4/7. That was fun. Next row times that column. 5/14 plus 18/14. 5/14 was 18. I think I got 23/14. Wow, I guess that's the answer. Again, you could have got that 10 minutes ago with some good old algebra, but I'm trying to explain a little matrix language here for you. Now we're going to try to apply this to differential equations. It won't be exactly like this, but there's a lot of basic matrix ideas in this, basic matrix review in this little video here. Okay, thank you.